In this video, we will be continuing with Unit 1.2. And we left off last time talking about different types of bonding. And in this video, we're going to focus on ionic bonds in particular. So what types of things have ionic bonds? Mostly non-living things, rocks, crystals, salts, even things like teeth and bones. Those types of things contain ionic bonds. As you can imagine, they can be very strong if we're thinking about an object such as a rock, right? But ionic bonds can also be relatively soft, such as chalk, something that crumbles apart fairly easily. And how do ionic bonds exactly form? So it's really a game of give and take. One atom is giving an electron, and another atom is taking on an electron into the valence shell. We're going to start out with an example of lithium and fluorine. So here we've got the valence shell structure here for lithium and fluorine. So lithium, if we go back to our periodic table, right? It's got 3 protons. And in order for that to be neutral, it has to have 3 electrons, right? So if we head back to this diagram, you'll see that we have 2 electrons in the first shell and 1 valence electron in the second shell. And remember, when we say valence shell, that's always the outermost shell that contains electrons. And if we remember before, we were saying that lithium could either, to get a full shell of electrons, which is ultimately what they want, right? There's 2 things that could happen. Lithium could either ditch an electron and just have a full first shell of electrons, or it could gain 7 electrons to fill that second ring. So that's the situation here with lithium. Now we move on to fluorine. So fluorine has 9 electrons because the atomic number of fluorine is 9. So 9 electrons cancel out those 9 protons. It has 2 electrons in its first shell and 7 in the next in its outer shell. Now here, fluorine is just missing 1 electron, right? It wants that full outer shell of 8 electrons. It is missing 1. So what actually happens here is lithium can give fluorine that electron. So lithium's got a full shell in that situation, and if fluorine gets that electron, it will have a full shell as well. So really, both atoms are then happy, and then that forms your compound of interest. So we're talking about this pretty casually right now, but there's a formal set of steps here that can be followed. So step 1, assess the initial electron placement for each atom when it is neutral. So do what we did, basically consider the atomic number of the atom, determine how many electrons cancel that out, and start getting more comfortable with drawing these valence shell diagrams. So we did that for lithium and fluorine. Electron swap, determine who needs to give away an electron and who needs to accept an electron. And we sort of show that here in our reaction arrow. Redraw the new electron configuration. So essentially redraw your valence shells, considering what was given and what was taken, which is shown here on the right side of the diagram. Determine the resulting ion charges due to the swap. So this we haven't done yet. So we always start out with these atoms being neutral, right? Usually. So the charge here is 0. And the charge here is 0. However, lithium gave away an electron. So its charge is now +1. And fluorine accepted another electron. So it's gaining more negativity. Its new charge is -1. And this is important. Step 4 is important for determining step 5. So if necessary, alter the number of cations and anions so the compound is neutral. And if you're unfamiliar with what a cation and an anion are, essentially cat positive and negative. So cations are positively charged, anions are negatively charged. So in this scenario right here, lithium is the cation, fluorine is the anion. Now, we always want our compound to be neutral. So we need to determine the number of each of these that would essentially cancel each other out. And for that, it's one of each. So we've got a +1, a -1, one of each will cancel out to 0. We have a neutral compound right here. So that's our first example here. Now, taking into consideration everything we just did, give the second problem a try with sodium and chlorine. So you can pause the video and work through that. For the sake of continuing on, I will come through and explain this, this solution right now. So when filling out the electrons for sodium in the valence shells, it will only have one electron in its outermost shell, right? And always referring back to this, sodium is in group 1, so it would lose 1 electron. Now chlorine has 7. Chlorine is very close to having a full valence shell. So the extra valence electron from sodium will go to chlorine. And then, so once chlorine gives away 1 atom, it would have a net charge of +1. And chlorine, having accepted an electron, would have a net charge of -1. And very similar to the previous problem, if you just have a +1 and -1 charge on both of these atoms, you only need one of each to cancel out and create a neutral compound, an ACl, sodium chloride. So this one's very similar to the first one. And in the next example, the importance of step 5 will really be emphasized. So take a moment, pause the video, try to work through lithium and sulfur. Okay, so in this scenario, lithium will only have 1 electron in the outermost shell, and sulfur has 6. So unlike chlorine that was just 1 electron away from a full valence shell, sulfur actually still needs 2, and that's evident here in the periodic table. It falls into group 6. So lithium, so after this swap, the extra valence electron in lithium will go to sulfur. However, lithium can only lose 1. So actually we will need 2 lithium ions to fulfill the needs of this sulfur atom in terms of getting it to a full valence shell, right? So we essentially, and this is drawn in this particular way just for convenience sake with lithium on each side, but you'll essentially just draw the same scenario twice of lithium giving up an electron to the 3rd valence shell of sulfur. Okay, it's very similar to the previous problems. Lithium started out as neutral. It gave away an electron, so it's +1, and it's the same thing on the other side. However, sulfur has now accepted 2 electrons. So its net charge is now -2. And so because you need, if you have 2 positive, if lithium is only worth +1, you will need 2 of them to cancel out the -2 from the sulfur. So that's why we've got Li2S. And that 2 in a chemical compound formula will always be a subscript. And if you're wondering could I write SLI2? Usually what you'll want to do is list the cation first, or the positive one, and then the anion, or the negative one. That's usually how the notation works for these compounds. So now take an opportunity, pause the video, and complete the last example with magnesium and chloride. So now in this example, magnesium will only have 2 electrons in its outermost shell, and chlorine only has 7. So the extra valence electron will go to chlorine. And so it's essentially the same type of situation. Magnesium needs to get rid of 2 electrons. And it will give 1 electron to each chlorine atom here in order for both chlorine atoms to have a full valence shell. So because it's giving away 2 electrons, it will have a net charge of +2. And because each chlorine atom is gaining an electron, those will both have a net charge of -1. So this is actually a little cut off here, but you would actually have 2 chlorine atoms. So you'd have a subscript of 2 in your end compound, taking into consideration step 5 up here. It would be magnesium chloride, but with 2 chlorines here. And so to summarize here, I just want to do a kind of a giver-taker scenario. So the giver, giving electrons, 1 atom from group 1 or group 2, but not hydrogen. Remember, hydrogen is the first atom on the periodic table. The taker, what are they taking? They're taking electrons. And those are usually atoms from groups 5, 6, or 7. And that makes sense, right? Because remember when we were annotating this periodic table, the ones in group 1 or 2 are usually looking to lose an electron or 2 because it's easiest for them to fill their valence shell. And those on this side, groups 5, 6, and 7, usually want to gain 1, 2, or 3 electrons. And the reason group 8 is not usually involved in this is because they already have a full valence shell. They already have those 8 electrons in the outer shell. So they're already happy and they don't usually partake in this forming of ionic compounds.